Hello, everyone. My name is TJ. I am a senior software engineer at Game Changer Media. Today, I'm going to be talking about something that I think is really topical and relevant for our times, and that is mobile video streaming. 2020 has been an interesting year. This, as you can even tell from droidCon, this is a droidCon that is completely online. So what used to be, almost taken for granted, whether you'd FaceTime other people, has become the primary way we do things. Whether you are at work, whether your child is home learning remotely, and so many other things. Even this conference, I'm sure, is powered by a variation of the software and stuff we're going to talk about today. So, without much ado, I'm going to be talking about mobile video streaming. And what we're going to cover is encoding, muxing, and publishing. All right, so let's talk about our contents. You're going to see a couple of acronyms here, AAC, H264. Don't worry too much about them. We're going to touch over it lightly. But as far as what you can expect from this talk, we're going to talk about the AAC format very briefly, the H264 format quite a bit in depth, an FLV container, RTMP, the Android pipeline to make all these things possible, and Kotlin magic, because after all, this is an Android conference, and we really love Kotlin nowadays. But let's talk about ways Kotlin actually makes some of these things really easy. Okay, let's talk about the AAC format. This is actually a very short slide because I don't really have much to say about AAC, and one of those things where I think it's a good thing where technology just works and you don't have to fiddle too much with it. It stands for Advanced Audio Coding. They have this logo. It's not the prettiest logo in the world, but it doesn't matter. It works excellently. It's the successor to MP3. And because as far as I'm concerned for streaming or my efforts of streaming, there's pretty much two types of AAC data that I'm going to be sending. I'm going to be sending a byte payload that has the audio configuration, things like the sample rate, the bit rate, and all of that. And then finally, the raw audio data is captured from the microphone on the Android device. And that's it, as far as AAC is concerned. Now let's talk about H.264. H.264 is an interesting format, mostly because of how dominant it is. There is H.265, the successor to it. And just 2 weeks ago, there was another format that even further compresses H.265 quite a bit. But H.264 is the dominant format, and it's everywhere. So it is the most ubiquitous video format. Its logo is slightly a little better than H.264's, than AAC's. It stands for Advanced Video Coding. I did. And then video compression is a dark art with lots of variables. And the thing I've noticed, because I did have to download the spec and read it through it quite a bit to, kind of find my way in it. At some point, like the biggest thing I came away with, I need to understand the basics because there's quite a lot of stuff in it. And it's a dark art with a lot of variables. And it's key to understanding some of those variables to be able to create a video stream effectively. All right. The key to understanding this, this dark art is something called the network abstraction layer. The primitive type here is a null unit, often abbreviated as null u. Let's talk about the null unit some more. So the null unit, there are quite a lot of them actually, and it's also really dense per bit. Each null unit consists of the first bit, which is always 0, 4-bit and 0-bit, which I think is an interesting way of calling it. The next 2 bits, which is the null reference IDC, this indicates whether a null unit is a reference field or frame. As far as H.264 goes, a reference field is a field that other null units in the payload have to refer back to. An example of this would be, and we'll talk about this more, things like independent refresh frames, because other frames are derived from the independence refresh frame. There's also things like the sequence parameter set and the picture parameter set. Again, we'll talk about this some more. But if a frame is a reference frame, this bit is not 0. Otherwise, it is 0. And then the last 5 bits that refer to the null unit type, specifying the raw byte payload sequence that follows this particular null unit. Okay, so let's talk about the types of them. It turns out, as far as the latest spec, there's quite a bit. It's almost overwhelming. I deliberately, this isn't very readable on slide. There's a lot of information because I do plan on condensing that. To all this to say, that's quite a lot of them. And the value in this case you're seeing is the 5 bits I was talking about in the previous frame. But we're going to, as far as we're concerned, we're just going to talk about this 5. There's the non-IDR, and again, IDR means independent decoder refresh. There's the IDR, SCI, SPS, and PPS. IDR again stands for independent decoder refresh, and what this means is, as far as video streaming goes, the one of the key techniques as far as compression is you have a full frame, and then within that frame, it contains all the information you need to display a picture, right? However, from consecutive frames, the idea being is to go from frame to frame. There's only a little bit differing per frame, so it's a waste of resources to try and send a whole picture anymore when you can just describe the things that have changed. So a non-IDR frame is a frame that doesn't have a full picture information. In other words, it contains a diff of the main IDR frame. You may notice every time you're seeking through a video, whether it's on DVD or on YouTube, no matter how finely you try to move the little seq bar, it will always take you back to a particular frame. And that is because that frame is an IDR frame. And you need to be able to decode an IDR frame fully to be able to show consecutive frames. SEI stands for Supplementary Enhancement Information, and this is information that just adds a bit more just gives more information to the bit stream. It doesn't display anything to the user. It could be, except maybe closed captions, but like it says, it's supplementary enhancement information. It has nothing to do with actually showing the picture. SPS and PPS stand for sequence parameter set and picture parameter set. And this has metadata, and because these are, key frames or key things that you need to decode the video. This tells things like the video resolution, the video height, the picture format, pretty much things you need to be able to decode an IDR frame. So an IDR frame depends on the SPS and PPS. The non-IDR frames depend on the IDR frames, and SCI is just extra metadata that you may want to embed in your bitstream. Okay, so that's a lot. Let's try to make sense of this bitstream, because if you open a hex editor or you open an H.264 file, chances are you're going to see something like this. And at first glance, this really doesn't seem to make a lot of sense. It's just a bunch of numbers. But if you look closely and you just start looking for patterns, you notice that the first couple of bytes in the sequence, you get a 0, 0, 0, then a 1, and then you have a byte payload, but then you notice that pattern again will repeat. You get another 0, 0, 0, 1. This particular is a screenshot of my hex editor. I use Synalyze it on a Mac. But you will notice that pattern tends to repeat itself. So why is this? Well, it turns out that H.264 decoders need to be able to identify the start of each null unit in the bit stream. Now, there are two popular ways of encoding H.264 in a bit stream. There's the Annex B format, which is what you see on the left here. Each null unit is prefixed by a 3 or 4 byte start code, 001, 0001. And AVCC, each null unit here is prefixed by the size of the null unit, typically 4 bytes, but not necessary. And AVCC is interesting because, for example, in Annex B, and when you're watching a live stream or live sports stream or something, it's more likely Annex B because this lets you seek anywhere. And when you seek anywhere in the stream, there's a new IDR frame and you can decode it. However, for AVCC, this is typically just sent once. And the reason why you do this is you want to use AVCC despite how difficult it is to parse, is that as far as sending the information goes, it is a lot more efficient. There isn't a lot of repetition in it. You only send what you need. Is extremely efficient for transporting the stream. For playback, though, you probably want in a different format just for the ability to see. Okay, now let's talk about FLV. The thing about FLV and other file containers is they have a simple philosophy. The philosophy is you pack it, we ship it for a low flat rate. Similar to UPS or any carrier, FedEx or whatever, you can think of, if you were going to come up with a metaphor, say you were moving in your house, you need to carry the movers, right? You packing stuff up, that's pretty much the encoding of the stream. And then you need to put it in the truck. Put it in the truck or wherever owns the truck, that's FLV, that's the container. So it's a container file format. You specify the information contained in it based on the spec and package the raw bytes accordingly. For example, audio tags, you can package audio tags in a variety of formats. However, if you're using AAC audio, you must sample this at 44.1 kilohertz. This is a very nice, fine piece of detail that I missed the first time when I was building this library. Because what will happen is I wouldn't put the AAC in 44.1 kilohertz, and it would work on the Google Pixel. But on every LG, Huawei device, it'll just crash. Samsung also handled it fine; it didn't crash. And it turns out I was like, I couldn't figure it out. One of our QA analysts, engineers was able to tell me that, this is always crashing. And then I decided to go look at the spec again. And I was like, oh, I'm not doing it 44.1. And then I did it 44.1 and it didn't crash. And the unfortunate thing about the encoders, the native encoders in Android is they're implemented natively and the crash doesn't tell you anything. You just get a very esoteric C++ crash. So that's interesting about FLV. For video tags can also be in a variety of formats. As far as H.264 goes, though, because FLV is a Flash video format and it was designed for streaming video, so it's no surprise that it doesn't use the more verbose, easy to parse NXB format. It uses the AVCC format. Okay, so we were talking about a metaphor before about moving house, and the carrier is FLV. Well, the truck that actually carries the things away from your house to your new place is RTMP. RTMP is the standard which we actually broadcast the stream, is how we transport the stream. So a note to Adobe, well, not necessarily because it was developed by Micromedia Flash, which was then acquired by Adobe, but it is a proprietary format for streaming Flash video. Adobe released this spec in 2012. It's TCP based, and it has an open source implementation called RTMP dump. But like if you actually wanted to use it as a library, it's mostly packed in this C++ library called librtmp. Okay, let's talk about the Android pipeline then, because we've just been talking about video, specs, formats, and other things, and this is an Android conference. As far as the Android pipeline is concerned, what you want to do, given the complexity of all these things, is you want to do as little as possible, as efficiently as possible. So as far as audio is concerned, you want to get raw AAC byte buffers from the device encoder. This is typically hardware or software. For video, you want to get raw byte buffers of picture data from the camera hardware. Now, as far as you may have noticed, like I was talking about SPS and PPS, this cannot change for the duration of the stream. Now, so if your video is a landscape, when you start the stream, as far as RTMP FLV go, it will stay. That tells the playback, whoever is playing back this video, to flip it. However, this is not very common because of one of two things. When you're transporting this video in FLV, when the device is watching it, the device isn't pulling down raw FLV. It's more likely using adapt HLS, right? Especially if it's an Apple device. Now, when you're converting from the stream and you're creating different, MU3A playlist for the HLS, there's a lot of things. A lot of this, the people that do the transcoding depend on a bunch of open source software. And as I've found, FFmpeg does not preserve SEI information. And because it's really difficult to preserve this information, it's not commonly used. Furthermore, even if whoever was transcoding your data actually preserved the SEI, on the other end of the field pitch, on the other end of the on the receiving end, the device has to also know to be able to parse it. Exoplayer, if you went to GitHub and you went to Exoplayer issues, they actually have an open pull request that actually does this. But I guess because of how niche it is, the project maintainers have just put it on the backlog, and it's been sitting there for about 3 months. But if you think this is something that's cool, maybe go start that issue. But for most intents and purposes, as far as Android is concerned, depending on the orientation the device is being held, you will ways you could do this. If you're good with OpenGL, you may want to use a GL surface view. I've seen implementations where it uses the, on the Camera2 API, there's an image reader class. The image reader will take the video format, the picture format, rotate the pictures, and then send it out. I found this to be extremely inefficient. So what I do is RenderScript has this really nice kernel render script is a hardware accelerated kernel process that runs on Android, and if you just describe a nice script, you can tell it to do things. So I use render scripts to actually rotate those image buffers before I actually stream it, and I find it to be extremely efficient. And the render scripts that I wrote for this are extremely simple. It's like less than, say, 150 lines of code. So ultimately in the pipeline, you want to efficiently rotate this image depending on the camera orientation and send it over the wire. Then you want to feed the excuse me. You want to feed the Android video. Sorry, I've got something stuck in my throat. You want to feed the Android video encoder an XB formatted images, an XB formatted bit streams. And when you do, you want to feed the encoder these images, and the Android encoder is going to spit out an XB formatted bit streams, which you might have noticed may pose a problem for us because we want our video format to be AVCC. We'll talk about overcoming that hurdle in a bit. But the pipeline looks something like this. You have a camera 2 input surface, a video source, audio source. You get everything, you mux it to FLV, and you publish it. So how do you actually publish? Well, you want to mux. I covered this prior. You want to convert the H.264 NXB bit stream to AVCC and package it as an FLV video tag, and also do the same thing for the AAC audio tag. Then publishing for Android, what we do is, like I already mentioned before, like RTMP is implemented open source in this huge thing called RTMP dump, typically packaged as live_RTMP. Well, it turns out because Android has the NDK, you can literally just take live_RTMP, dump it, into your Android project, use the NDK to build it, and call the live_RTMP methods from a Java native interface. And just like that, you have a video streamer without any extra work. You don't need to implement this yourself. It's already been done. So where do you go from here? You just profit, right? You've built a simple streaming pipeline doing as little as possible. In fact, the most complicated part of this was not even the muxing. It was the render script image transformation, which itself turned out to be very easy. So just like that, you have a video pipeline. And this is what we use at Game Changer. We call it the GC Android Streamer. And this is how we actually power live video in our app. A note about muxing and format transforms. This is one of my favorite emojis. It is simple, but very particular, and you'll learn why I use this emoji in a bit. The decoder needs to be fed information about the video and audio is decoding, and you must transmit this first and once, not more than once, right? So for AAC, it's the audio config. For H.264, it's the SPS and PPS. Which, funny enough, if you write SPS and PPS, it looks like you're calling out to your puppy, like, psst, psst, come here, puppy. But I guess that's just what happens when you look at the same bit of code for entirely too long. You also must be aware of the timestamp. For as far as FLV goes, each frame has a timestamp, and this timestamp must increase monotonically and consecutively. It must always go up. Ideally, like I mentioned before with Exoplayer, rotating the image can be skipped by providing SCI, but this is niche and very rarely used. All right, there's a lot of talk about video formats, and this is an Android conference, so let's bring it all the way back to Kotlin. So I had to build this pipeline using Kotlin. And Kotlin actually afforded me quite a lot of advantages and lots of easy ways to do things, and I'm going to highlight a couple of them. So we're going to talk about delegates in Kotlin, timestamps, and denial of service attacks, inline functions, ON algorithms, format conversions, because again, we had to convert from the Android encoder is going to give you the bit stream in NXB, and we want it converted to AVCC as efficiently as possible. We're going to talk about the Java, the Android NDK, Java interop with Kotlin, and code reusability. And we're going to talk about coroutines, which, I am an Alex Java aficionado. I still think functional reactive programming is amazing. But I do find, like, the simplicity of, a suspended function versus like a single or maybe, it cannot be overstated. All right. So delegates, timestamps, and DDoS. This is for video streaming. Our company partners with a company called Mux, and I actually brought down their servers. The feedback was, I am sending events faster than real time. So what I was doing is for each frame I was sending, my timestamp was off by a factor of about 10 or so. And their backend their transcoder was trying to mux this quicker. And then, it just corrupted a bunch of assets, brought a bunch of things down. It was terrible. It was a bad time. Really embarrassing for me as well. But let's talk about Kotlin delegates. Now, delegates are like a factory for values. The most common delegates of Kotlin are the lazy delegate, where it's only going to create a variable at the first invocation. Observable delegate, where as soon as you set a value, it's going to notify something else. It has a callback to notify something else. And map, where you could just delegate values to being read from a dictionary or a map. Now, the thing about delegates is that perfect for encapsulating often use software patterns that can provide a value. Now, I had an issue. When I am feeding the audio encoder, I want to give it a timestamp in microseconds. When I am muxing FLV, I want to feed it a timestamp in milliseconds. Ultimately, though, the basic thing was I have some start time systemed on nanotime. I want to subtract the current time to figure out what the timestamp is. Can I write a delegate for this? It turns out yes. So let's look at what an implementation of a timestamp delegate would be. We have an internal class, timestamp source. You give it the time unit, which is a very handy Java enum. I could start with some initial value 0. My recording start is just going to be systemed on nanotime. And the thing about delegates is that you have to override this get value method. So what I can do is I can just try to get my next value with this next function. The implementation follows shortly. But again, I said the timestamp has to increase consecutively, and the Android audio encoder can call you to actually feed it multiple times within the same time frame. And if it does this multiple times within the same time frame, it just tries to grab a bunch of data at once, you have to increase the timestamp. So this atomically would just grab the value that it currently has and just increases to make sure it always increases monotonically. Atomically, lots of buzzwords I got to familiarize myself within the process of doing this. And then value is equal to the next value, and then I can then return that value. This is the implementation of next value. But the cool thing here is next is this simple function where it just takes the time unit you passed in. So this timestamp delegate has nanosecond resolution, subtracts the time I start recording, and then convert it to the appropriate timestamp. And now I have this nice, simple delegate for getting time in milliseconds, microseconds, seconds, days. It really doesn't matter. And this has let me write code as simple as where if the declaration of this timestamp is going to be timestamp by the timestamp delegate, and I can just write simple code like this without having to call another function or write a new class and call it timestamp creator or something, or some other Java pattern that has come up to solve this issue. Next, I want to talk about inline functions, ON algorithms, and format conversions. Now, it is imperative to have an abstraction to transform a bit stream on the now unit level, because there's a lot of things you may want to do. So, you may want to filter stuff, you may want to add stuff, but it's imperative to be able to operate on a bit stream on a now unit level. Now, in my case, and for many, I wanted to be able to convert from NXB to AVCC bit streams. Now, I could technically encapsulate this with a bitstream mapper or bitstream converter class. Or should I? So I thought about this for a bit, and I was like, is there something better that can communicate what I want to do? I have a bit stream. This bit stream could be in a variety of containers. It could be in a list. I could have a list of bytes. I could have an array of bytes. I could have a byte buffer. Do I really want to, create a new class? Surely the type that already exists already has all the information I need. Turns out with Kotlin extensions, you can do something like this. I'm going to talk about a couple of things. I'm going to talk about like a type alias. I'm going to call this a byte random access. In other words, this is a container of some type T, and I need to be able to just get a byte at in constant time from a certain index. Given a certain index, I need to be able to grab a byte from this thing. This is, quote, a byte random access. Now, if I have a byte random access, I can easily write an extension to extract a null start code from this. I can do this. The algorithm, the implementation of this is 03, 04, effectively 01. And pretty much the algorithm is look at the first byte. Is it a 0? look at the next byte. Is it a 0? And if any of these don't match, it's not, this is not a now start code. So look at the next one. Is it a 0? Is it a 0? Is it a 1? Then I have a 3-byte start code. Is it a 0? Is it a 0? Is it a 0? Is it a 1? Then I have a 4-byte start code. So at each index, I'm going to do this 4 operations. But this is as far as it's constant time. Next, I can define another algorithm to figure out the index of a start code within this arbitrary container, and cap it at the end of the size of this container. Now, this technically is ON because I have to look at every byte in this container to figure out where the now start code is. However, because I'm collecting all this data from the encoder, and the encoder already has this in an NXB format, this can be thought as effectively ON, because as soon as the encoder spits it out, the first index is always going to be now start index. Then there's the raw byte payload sequence I have to go through to find the next one. But this ultimately, this is constant time. There isn't a cost penalty for doing this too much. Finally, now with these two defined, I can then describe an extension function called on each now unit. And I can do this on an arbitrary byte random access container. And I can just do this. I can now write an operation that lets me do something on each now unit and a byte array, a byte buffer, or a list of bytes. So let's talk about implementations of this. And here, where now accessor is just another type alias for a function that does something with the start code. Okay, so muxing from byte buffers. How to actually use this byte random access. Now, the Android encoder is going to, whenever it decodes H.264, encodes H.264, it's going to spit out a byte buffer. When I want to mux this byte buffer, I can just call, so my accessor in this case is just a byte buffer. I have a byte buffer. I can just call this buffer on each now unit. If I don't have SPS, in other words, I haven't sent it out, I can do something. Now I have my SPS. When I don't have, now PPS has to follow SPS as far as FLV is concerned. So if I have SPS and I don't have PPS, I can do some operations. Now I have PPS. Finally, if I have both SPS and I have PPS, I can now push out my video frame. And this was all being done with, this simple extension on each now unit. So pretty much what I'm doing is inline. As I'm muxing in inline, I am converting from NXB to AVCC in near constant time, right? So this inline function, because where I'm using this, I'm not really creating any classes. The Kotlin compiler is just going to inline the implementation of the on each now unit extension and just drop it inline and right here, and I can literally convert from one H.264 format to another as I mux, which is extremely efficient and is really, really useful. Another case where I want to do something like this, though, is when I'm testing. When I want to actually write a test for my FLV converter, my FLV muxer. Now, typically, when you write a test, you usually have, some static resource. In my case, in the repository, I have a sample 264 file. When I use a class loader to get the resource as stream and read it as bytes, I now have a byte array. However, the byte array is, quote, a byte random access because you can just access a byte looking at each index. So I therefore now I can write this in Kotlin, this compiles, I can just use an extension function, the get method on the byte array class, and that magically is a byte random access. So byte array :gets dots on each now unit. I have a start code, I have the index, I have the size, I can do whatever assertion I want to do, just by virtue of modeling, the on each now unit, by modeling it as an extension on the generic type rather than creating a class. Let's go even further. Sometimes in your bitstream, you want to be able to augment it. You've got the video, you want to do more things to this video. What you can do, like, for example, is you want to write SEI, you want to add a supplementary enhancement information, where maybe you want to provide closed captions for people that are hard of hearing. You can come up with a class. I call this premiux in my testing. So there's two different types. I have a byte buffer. Sorry, I'm speeding up a little bit, just trying to manage my time here. I have a byte buffer. You can ignore most of the code that's here, but the point I want to make is you can give it a rotation. If the rotation is there, I have an XCI extension to add display orientation. In my case, this could be a closed caption information. But once I do all of this, I can literally just say like my data size, depending on if this information is there or not. I can add another start code, add the supplementary enhancement information size, and then now the size of this premiux is the size of the raw byte buffer and the extra metadata that I want to add. Now, because ultimately what I'm trying to create is a different implementation of a byte random access, when I actually want to get information out of this, the implementation is just, again, using Kotlin's incredibly powerful pattern matching. If my now start index is within 0 and my SEI, I'm not going to actually read from my byte buffer. I'm going to read from the SEI information. And I can do this and then just again, notice this is constant time because all this premiux is a wrapper around a byte buffer and some extra metadata. So inline, I've added stuff to my bit stream without doing anything else, right? Without creating any new objects, in fact, because the premiux is just a wrapper every time I get a new byte buffer. Of course, this is in a single threaded application. Or at this point, the application is single threaded. But I have a premiux, I have a new byte buffer, give it, set the byte buffer reference in the premiux class, add the SEI, and when I'm actually trying to mux and I'm pulling things out, I'm doing this pattern matching, and that lets me just augment and just add random data, add random SEI to my bit stream in real time without having to create a new byte buffer or wrapping more data. I can just augment and do whatever I want to my bit stream at any point in time. It's extremely powerful. And then the implementation of the premiux byte random access, again, is just byte random access premiux, and it's just a method reference to the premiux class. Very powerful, very concise. For the NDK Java interop and code reusability, like I said, the important thing was to delegate everything to librtmp. It exists and it's great. Using the Android NDK, I can bundle it easily into the app. And since there's 100% interop between Kotlin and Java, all JNI methods can be called easily. So as far as our app is concerned, when it actually comes time to, we've done all this transformation, we've done all the things we want to do, when we want to send this information out, we just literally have this simple RTMP publisher class. And then all it does, sorry, I don't know why my computer did that. I can just power through the rest of my slides. Pardon me. All right, so all it does is we have this native methods in librtmp. We load this RTMP publisher class, and we only have 4 things. You can open an RTMP stream, you can write an FLV frame, you can close the socket, the TCP socket, and you can check if you're connected. And that's all we have to do. So coroutines, concurrency, and callbacks. So I saved this for last because this is one of my favorite things. This is the coup de grace. So Android Camera2 API is notoriously difficult to work with. It is, however, though, a fairly stable and sensible API. It just has a lot going on. If you look on Stack Overflow, some people say, oh, I just have to add a random delay and everything works. But I was like, this thing has to be more predictable than this. Random delays don't make sense. So I realized the Camera2 API has a bunch of callbacks, like on camera ready, on camera active, on surface created, a bunch of things that is just hard to reason about. But what if you model this callback where you can get a callback from resume on active and all these things? What if you just model them as a stream of events? If you do model them as a stream of events, you can suspend the invocation of your method till you get the event that you're waiting for. So in other words, you can now have this status of the Camera2 API where you have an error, ready, active, closed, surface prepared callback. And if anyone has used Camera2 APIs, you notice that these are named identically to the callbacks in Camera2. So you have an unactive callback. I am using a Kotlin experimental feature, a mutable state flow, where you can just grab the flow and you set the value to whatever the callback provides. This is powerful because you can now suspend till the next invocation. So I have this extension, inline function, verified R, so the generic type R, is known. And then I want to suspend till the next status, but then I have to pass it a trigger that will trigger the next status. And I can skip everything till I get a layer to the status. The important thing is I have my current status, I invoke my trigger, and then when the next status flow, I now notice I am now collecting the flow in the suspend function. I filter it, I say it's not the current one, and I wait for it to be the generic type R I'm interested in, and I get the first thing that is returned from that. And this now becomes a suspending function. So in other words, I am suspending till I get the callback I want. And then if it's an error, throw an exception. If the camera was idle, this shouldn't happen. Idle should only ever be the initial value. But now I have something that will suspend till the next time I see something. With this implemented, how do I actually use this? For example, I want to check, for example, when I was streaming, was the camera previously being used? Was I previewing and did I try to stream? What I can now say is, again, this is in a suspending context. If my camera status is not active, I'm going to suspend till the next time the camera is active. And the camera is going to become active after it starts processing the repeating request to start a camera preview. And that is extremely powerful. Next, let's say I want to start previewing and I actually want to start recording for streaming. Well, I can get my camera session and then I can suspend till the camera is ready to receive more requests. And my trigger is abort capturing the preview. And then this method will suspend till the camera is ready to start accepting another request. So at this point, at the time this method resumes invocation, as soon as the suspension is off, I can now suspend till the next time the camera is active. It's actually actively processing my request, and my trigger is set the repeating request to record. And by the time this function resumes, I am now resuming. And this predictable state machine is what really powers this streaming experience. And it's extremely powerful. I can't summarize or describe how powerful and useful this is. Okay, so wrapping up. All of this, if you want to see it in real time, is actually available in the latest version of the Team Manager app. We have a streaming tab, you can create a team, and all this is available to see it. We are working on putting some finishing touches on the library, and we will open source it at some point. But this ultimately powers a live video stream. In fact, as far as droidCon is concerned, if I wanted to, this whole process where I have my camera and my laptop and a webcam, I could technically, with the same Zoom link, I could just put the link on my phone and actually start streaming from my phone. I'm going to check how much time I have here. I would like to show a demo in real time. Okay, I think I'll take a couple of questions though before I try to do that. And that is what I have for video streaming in Kotlin coroutines. Kotlin, are there any questions? Can I recommend a good GitHub to follow the best practices with an API where we can play with different streaming types so we can play with it and understand how everything works? So when you say streaming types, do you mean RTMP? Do you mean you mean like the streaming technology? If that's what you mean, there are two. One of them is called, if you put the keyword YASEA in Google search, it'll come up with a GitHub repository. That's an acronym for Yet Another Streaming Encoder for Android. It's really old, and it uses the Camera2 APIs, but this is where I started to get my feet dug into the different ways you can actually try to get video information out of Android. There's also one by a gentleman called Pedro. I forget the name of the repository, but it's a pure Java implementation of RTMP streaming as well as other formats. I elected not to go with this though because personally I felt there was a lot of garbage collection in the pipeline and I could do something more efficient, which is why I went with this. And then I delegated to live-RTMP. But as far as Muxin goes, the Muxin implementation was a very good implementation, which interestingly enough, its Muxin implementation was based on the Muxin implementation in Yet Another Stream Encoder for Android. So those two repositories are really where I dug my teeth in. Yet Another Stream Encoder for Android, YASEA, and the other one is, I think if you do Pedro RTMP streaming, that repository will come up. And of course, as soon as we open source the Game Changer one, I'm going to be extremely biased because I wrote it, and I'm going to say that's a good one to look at. Is creating HLS streams on Android supported? Also, what is the reason behind using RTMP instead of HLS? The reason you'd want to use RTMP instead of HLS is because RTMP is, it's extremely efficient. There's a lot of stuff that, goes as far as video streaming is concerned that RTMP already takes care of for you. It's also like when I was talking about the difference between the NXB format and the AVCC format. RTMP, and because it uses FLV, already takes quite a lot of that, does a lot of that for you. However, when you actually want to watch the video, you do not want to watch a raw RTMP stream because the device's internet connection may vary and stuff. So what you want to do is you take the RTMP, you only use RTMP for publishing. So you publish it to your transcoder. The transcoder is going to ingest our RTMP stream, and then it's going to create an HLS M3 UA playlist. And that playlist is just a bunch of segmented chunks of data. And then for the person watching it, depending on the video connection, they could jump between one or the other as their bandwidth applies. So RTMP is great for delivering for further processing, but you don't necessarily, you could, but you don't necessarily want to watch back an RTMP stream. Any tips on how to implement an RTSP client on Android? Any high-level plays? Our ExoPlayer does not support it. ExoPlayer is very opinionated on a bunch of things. Unfortunately, for when I was working on this, I was really looking at the transportation part because for what we're doing, we already knew we wanted to play back HLS. So unfortunately, I do not have anything on how to play data from a raw RTSP stream. RTMP, since RTMP uses a FLV container, I think if I was going to start looking at that, the first thing I'd want to look at is what is the container format used in RTSP? And if the container format is RTSP, I'll just look at, because ExoPlayer supports RTMP playback, and if they use similar contents, I would advise to go look at the source of ExoPlayer and see how it plays back the raw RTMP source. Spoiler alert, when ExoPlayer plays back the raw RTMP source, it also delegates to librtmp and RTMP dump, because I think it's general. A lot of people think if something has been done, there's no need to reinvent the wheel unless in any case explicitly requires it. So I'll say read up the RTSP spec, figure out what file container format is used. The file container format, ExoPlayer probably supports that already, so you need to find a way to unwrap it and play with ExoPlayer. I really like my talk, but there's a lot of information that I liked about what I talked about. Where can a newbie find information about that? So for me, because I was a newbie before I did all these things, I found all that information on Stack Overflow. And pretty much, but the thing about, you find out that the video gods, as I call them at Stack Overflow, they guard their knowledge jealously. They guard it jealously, not that they're not willing to share, but before they share, they want you to have done some work. So ask intelligent is probably not the right word, ask detailed questions on Stack Overflow. And one of the benevolent video gods will see you and your cry for help, your cry, you just yearning for information, and they'll point you to resources to where to look. And then after I, found my feet there, the next thing I had to do was I really had to download the H264 spec document from the knowledge body that guards it, the people that come up with the spec. And I actually had to read that document, and I had to read it for quite a bit. And it's a huge document. So if you're a newbie, find your feet by asking questions or looking for questions on Stack Overflow. There are a couple of people there that just kind of hover over the H264 tag and will tell you where to go, but you have to be detailed and say exactly what you tried. And then after you find your bearings, from these benevolent video gods, download the spec and read through the spec. Okay, sure. Thank you all very much for your time, and I hope you all have a great morning.